All right.
Hello, good afternoon. My name is Allison Bamberger, and I am the program director here at the Masonry Institute of St. Louis, and I would like to welcome you all to our final seminar of this season. Thank you so much for being here today. We have our seminar on seamless transitions, perfecting material changes in masonry design. You can see this is our program description. It's right there in your packets as well. And you'll see our learning objectives. We're going to detail conditions and horizontal bands of clay and concrete masonry, calculate brick masonry expansion, calculate concrete masonry shrinkage, using rules of thumb and alternative engineered approaches, and decide which movement or when movement joints are needed in residential construction. And this is a course that is offered with AIA. And today we will be passing around our box for your business card because we will have a book on assessment and retrofit of masonry structures written by none other than our speaker today. Yeah. So if you win, I'm sure he'll sign it afterwards if you ask nicely. No, but first I want to introduce our staff. In the back over here, we've got Greg Bryant. He's with our Masonry Structural Coalition. Of course, many of you know Bruce Augustine. He's our technical director. Someone you probably don't know is Josh Leone. He is our newest team member here. He is our residential specialist. And Dave Gillick was walking around here somewhere. You probably saw him with the iPad. He's our executive director. And of course, today we are sponsored by Best Block, a partner that we lean on for quite a bit. They're a great partner in everything that we do. We've got Mark Wilhelms here to give you just a little idea of what they've got going on. Mark?
Yeah, well, thank you, Allison. First off, just thanks to the Masonry Institute. I travel the country now, and this doesn't happen everywhere. I mean, how many programs this year? 22 programs trying to get everybody up to speed. You don't realize what we have sometimes until you don't have it, so thank you. Just pleased to provide the lunch today, and I want to introduce Chuck Davis. Chuck is our architectural representative. If you haven't met him yet, Chuck works here locally since I'm more nationally now. And then also in the back, we have some boards set up just with our best brick material. We've been making this stuff for 40 plus years, and it still continues to find new life as a structural single white wall system. As I look at Scott and Randy out there, and we've done some Walgreens stores over the years with these and still hanging around. So thank you.
Thank you folks so much. We appreciate you.
Thank you.
And just again, I want to reiterate a thank you to everyone. This was my first seminar season here. I have really enjoyed it. I appreciate everyone who gives us feedback by way of our survey, which you'll get a link to tomorrow morning. We really appreciate that information, good, the bad, the ugly. As we go through the summer and we plan for next year, that information is really going to drive how we plan moving forward. So thank you all for that. And we hope to see you in September. You'll get next season's schedule in the middle of the summer sometime. So we hope to see each and every one of you many, many more times next year. So thank you. And without further ado,
Right.
Yeah.
Thanks, Allison.
Schuller. Thank you.
Well, we've got the good and the ugly handled right here. Nothing bad today. I can handle that. Well, yeah, it's a pleasure. Thanks for having me out here. It's been 2 or 3 years since the last time I was out here teaching a class. I love coming to St. Louis because it's always a full house, and maybe part of it's a free lunch. I don't know, but it's whatever it takes to get people in the room learning about masonry. That's important. So yeah, talking about transitions, what we do between different building materials, and we've gone through our learning objectives. We've seen that already, but I've got a couple images of some recent winners of Masonry Industry Design Awards. These came from the Mason Contractors Association website. And if you look at the winners in recent years, almost all of them have this mix of many different materials in their facades. And so it's kind of a recent architectural style, last 10, 15 years or so, trending towards mixing these materials. So here we see stone, we see brick, we see concrete block in our facade, our masonry materials, but also putting in metal, putting in wood and concrete elements in there. And you can do this. I mean, you can mix these materials in these ways, and it gives a nice attractive appearance, but we have to be aware that there are some special design considerations to worry about. Our materials are going to move differently in response to temperature and moisture and loads. And so our job as designers is to be aware of these different movement concepts and detail our transitions to accommodate that movement, but also keeping water, keeping air outside of our building. So we're going to talk about detailing quite a bit today. And let's see, let's try the big button. There we go. So yeah, here's what we're going to talk about, just looking at different material types, transitions between different types of masonry to concrete, different support conditions, and just a little bit at the end about residential, more of an editorial comment than a technical one. We'll get to that later. So as I said, you know, there are two keys to designing our transitions properly. We're going to accommodate movement, differential movement, we call it, and dealing with moisture, okay? And looking at what is the standard of care these days, what does the building code require? We're not going to talk about transitioning to vegetation. We don't want to put these things in our walls. Gosh, I can't imagine what's going on inside that building. It's a garage. It's an old garage, but vegetation growing out of our walls. So why are we designing transitions? Well, we do it because the building code says we have to. It's our job. And 3 spots in the TMS 402 code, that's our building code requirements for masonry structures. We've got way up in chapter 4, general design requirements. It's our job to consider all these things, including differential movement. And in chapter 13, right, this is our 2022 code. Our veneers are in chapter 13 now. We're going to design and detail our wall systems to meet the requirements of the legally adopted building code. It used to be simpler. It used to say design and detail our veneer to with flashing and weeps. Now we're just meeting building code. We're also going to design and detail our veneer to accommodate deformations, differential movement. So we're doing these things because we're required to. Plus, it keeps us out of trouble. And we're going to spend a bit of time today. You know, a lot of this class is about differential movement and how our materials move and calculating that movement, detailing, reinforcement, and all. And I think I hope most people understand that brick tends to expand over time. And I've got a nice little photo here of a brick veneer. We've got a capstone element up on the left. We've got a window frame up above. Brick is expanding towards this expansion joint, all right? So we've got a joint at the end of our brick runs to accommodate that expansion. The sealant is all compressed. This is what happens as our brick responds to moisture, as it responds to temperature, okay? What else do we notice in this image? There's something else that's super important. What do you see? A little separation. I'm going to draw with my little mouse here. Let's see how that works. Not too bad. There's a crack right in there where this veneer is moving a little bit separate. The sill is moving separately from the brickwork below. So that crack can let in water. All right, so as long as we have our drainage cavity detailed properly, we've got flashing, got weeps, and all our things down in the cavity, we can deal with that water that gets in at that separation. So 2 main types of movement. Number 1, we have temperature response. Okay, our building materials move in response to temperature changes. And here's a nice little table of different thermal expansion coefficients. These are in millionths of an inch per degree Fahrenheit. And I don't know, it's kind of tough to look at numbers. We're going to look at this last column here. Oh man, I can almost draw an arrow with the mouse, not very well. But this last little column here, what I've done is put in a design temperature differential of 100 degrees Fahrenheit and calculated the movement in a 100-foot length of wall. Just as a kind of a realistic number. So our brick and our block under 100-degree temperature change is going to expand about ½ an inch. Concrete a little bit less. Sandstone has a pretty wide range of movement potential. It depends on the type of sandstone, if you have a quartzite binder or a clay type binder. Limestone, those numbers come from the Indiana Limestone Institute. The brick and the block numbers, those come out of the building code. Okay, so we have a range of movement, about a half an inch every 100 feet, maybe more with concrete and sandstone, limestones all over the place, depending on what type of stone you have. Steel also moves, okay, in response to temperature. And if that steel is rebar encapsulated in grout inside our walls, it's no problem. Okay, it's close enough, the thermal expansion, the rebar is close enough to our surrounding materials that we don't have to worry about any cracking there. But if something different happens, if we have our steel elements exposed to the exterior, and I've seen this on supermarkets, here in automotive repair shop, and look at all those garage door openings, each one about 12 feet wide. We've got 1, 2, 3, we've got 5 of those, about a 60-foot run of steel framing there. And the designer did a great job designing movement joints. We'll get into that a little bit later, but we've got movement joints. See the shadow lines at every little pilaster above the openings. So the brick's in great shape there. But think about that steel lintel that is exposed to temperature. It's going to heat up and cool off much quicker than that structural brick around those openings. And so we're starting to see some movement, particularly at where those steel beams are tied into the surrounding brickwork. And what happened here, we've got the steel shrinking, expanding in response to temperatures. The design had these rigid studs tying that steel into the structure around there. And if you look close, well, or not, you can see some cracks. We've got cracks around here. We've got cracks around this location. So again, differential movement. Steel is moving differently than the wall. What's the solution? Well, we came in and let's cut those studs free. Up here, we put in a little slip angle connection, just have a bearing seat for that beam, and that way that steel in the brick above it can move independently back and forth, independently of the structure itself. So we got to think about this. It does come up from time to time. Our building materials also respond to moisture. Hey, this is reversible moisture movement with a lot of our materials. We know when wood gets wet, it swells, right? When wood dries, it shrinks. So if we're embedding any kind of wood element inside of masonry, well, make sure that there's a slip joint. Otherwise, we see this crack developing here. This is actually a manufactured stone veneer. I don't think a real stone would crack through like that. So our cement-based materials have a tendency to shrink over time. As they lose moisture, as the cement hydrates, there's a chemical reaction with the cement that tends to cause those cement-based materials to shrink. So it's concrete block, it's concrete. Brick expands over time. Okay, we know it. Second that brick leaves the kiln, all the moisture has been driven out by the high temperatures of firing. So that brick is out of the kiln, it's absorbing moisture out of the air, out of the environment, and it tends to expand more than you'd think. A little tiny bit, but more than you'd think. So if we look at our movement concepts, our moisture-related movement of these different materials, our moisture expansion looks like this, a similar table. There's no temperature involved, but this is just inches per inch times 10 to the minus 4. Then again, I don't know, those numbers don't mean much. So let's look at the third column. If we have a 100-foot length of wall, our brick is going to expand a little less than 3/8 of an inch due to the moisture uptake. It doesn't ever shrink again. Okay, this is a permanent, one-time, irreversible expansion. Block, concrete, sandstone, limestone. Block and concrete tend to shrink over time. Okay, about the same order of magnitude, but instead of expanding like brick, it's shrinking a little more than 3/8 of an inch over its life. So this differential movement is important to keep in mind. Wood, we'll talk about wood in a moment. Got some things to think about with wood. So for brick masonry, if we're calculating our brick movement, again, this isn't supposed to be a seminar on expansion and movement joints, but we have to understand it. So we've got brick masonry. My best design guide for you is to go to the Brick Industry Association on their website, download for free this technical notes. Technical note 18 and 18A talk about movement joints and brickwork. and they have a pretty straightforward calculation. Okay, our movement is related to coefficient of moisture expansion, our temperature, our expansion, our coefficient of thermal expansion multiplied by a temperature range. Okay, there's also freezing expansion. Most of the time, though, we don't take it into account because for that freezing expansion to, I'm going to cross that out a little bit, for that temperature or that freezing expansion to occur, the brickwork has to be more or less saturated. Doesn't happen really in service. So we, unless you have like a parapet or retaining wall, so we don't take into account freezing related expansion. Our temperature, our change in temperature, a lot of times we'll use 100 degrees Fahrenheit. We'll use that in a little example here as a suitable design temperature variation. And some people use 140 degrees. I think 100 degrees is a nice round number that we can understand. So neglecting freezing expansion, right? We're putting that at 0 here, down here. We've got a little bit of movement related to irreversible expansion. We've got another bit of movement related to the temperature change. And what that tells us, if we're putting our brick movement joints at 20 feet on center, our total movement in that 20-foot length of wall is about a little less than 1/4 inch. Good to think about. It's more than you might think. But also that 0.22 inches is a very real number. Brick does expand like that over time, and that means with brick we have expansion joints. If we're detailing expansion joints, we've all done it, right? We know expansion joints have to be free and clear of any material in there that's going to block that movement. So we can't run joint steel through that expansion joint. Okay? We're going to cut that steel short. We can't have mortar. We can't have like wood filler strips or anything in that joint. About the only thing you can put in a brick expansion joint is something compressible, like a foam pad, neoprene pad. Best option, just leave it open. We're going to seal it at the face of the wall with the sealant and backer rod like we have here in that detail. And that gives us a space for that brick to expand into. What's the mantra? This is always on the test later. Brick expands over time. Now, we don't have tests. We're not, but when we're teaching students, yeah, it's always, we always have multiple choice. It's really simple. Brick expands. What kind of sealant are we going to use? Well, grade NS. What's NS? Non-sag, right? What about use type M? What's the M stand for? A lot of people say use M as masonry. Well, kind of. You can say that. Use type M just means that sealant has been tested in conjunction with masonry mortar, using the standards and all that. But use type M for masonry. Most of the time, a class 50 joint sealant is what we want to use. That class 50 tells us that sealant can compress by 50% without causing any failure of the sealant. So from a compatibility standpoint, we'll use silicone sealants very often for use on brickwork. Polyurethanes also work. Polysulfides, I don't know. I don't see those around as much anymore, but longest lasting usually is going to be a silicone type of sealant. So let's think about, so that's brickwork. Concrete masonry does not expand over time. Concrete masonry actually sees a net shrinkage over time. We can see a crack that's formed at the edge of this lintel. Right? Look, you can kind of see it on the screen. I'll kind of draw it in here. Our shrinkage cracks tend to form at areas of stress concentrations around openings, windows, lintel bearings like we see here. And our job as designers is to understand that movement, that shrinkage. And there's some special design steps we have to take to make that shrinkage occur where we want it. We want that shrinkage to happen at control joints, different from expansion joints. So we have control joints that are really just a weak spot in the wall. Okay, unlike expansion joints, we need a space for the brick to move into. Concrete masonry, we're just going to form a weak spot in the wall so that when our block shrinks, the movement occurs right there where we can deal with it. Nice NCMA. Well, actually, it's CMHA now. It's going to take me forever to learn that, to relearn my brain. It's not even a proper sentence. To relearn what's in my brain. How about? Masonry and Hardscapes Association, Concrete CMHA. look at their website, you can download. They have a couple nice tech notes on designing movement joints for concrete masonry. There's two approaches. The empirical approach, meaning we don't have to do any calculations. We like this approach, and it works just fine. We're going to start by putting our concrete masonry control joints where we need them, a little bit more on that later. We're going to put intermediate joints at a 25-foot max spacing. What's wrong with 25 feet? Concrete masonry. Not modular. Right, so they've changed it recently to 25'4", so right down in your little slide, 25'4". That's our maximum spacing for control joints in concrete block walls. Modular. Okay, working off of an 8-inch module with CMU. So we're going to split up our walls in these 25-foot segments. We're also going to make sure that we split our walls up into rectangles where the length or the spacing between our joints is no more than 1.5 times the height of our wall. So if you have a 10-foot wall, 1.5 times that, 15 feet, we're going to put our movement joints at 15 feet on center. Okay, these little rectangles. The third step is designing and detailing reinforcement. We're going to double up on our joint steel like we see in this detail below here. We're going to have joint steel above and 2 courses above. We're going to have joint steel 1 course below our opening, and we're going to put vertical bars at each jamb. We know that stress concentration, that window opening, is going to force cracks to form there. So we put additional reinforcement there to limit the opening of those cracks. And generally, 9-gauge joint steel at 16 inches on center is kind of the standard. So regardless of if we have reinforced block, if we have a concrete block veneer, any kind of concrete masonry construction, we need to be putting our joint steel in there to help limit cracks that might open due to shrinkage. Pretty simple. We can also follow an engineered approach. That means we actually calculate the amount of shrinkage, we design our crack width, and we know that, and our steel to accommodate or to limit our crack opening. There's 3 types of shrinkage that we have with concrete masonry. There's a linear drying shrinkage. Okay, when concrete block are made, it's a dry cast wet. There's not a lot of moisture in there, but there is moisture associated with the block, moisture associated with curing. So as that block loses moisture, and as the cement hydrates, there's shrinkage. That happens in months or so after manufacture. The second component is carbonation. That's a long-term action. That's as carbon dioxide gets sucked out of the air into the cement byproducts within our block. There's a carbonation-related shrinkage. That happens months and years down the road. And there's thermal shrinkage as well. And so, I don't know, for whatever reason, we use a different temperature range for calculating shrinkage, about 70 degrees. And we come out to, bottom line, the CCC, this crack control criteria, about 0.00118 inches per inch. What does that mean? That same 100-foot wall, we're going to have about 1.4 inches of potential shrinkage. A lot of movement in a 100-foot wall. Control joints, reinforcement. So how do we get to that next step? Yeah, I forgot I had this note in here. If you look at the building code requirements, they'll say this total linear drying shrinkage, we're going to use half of that value, about 0.00032. It's because the way that concrete block are tested to determine drying shrinkage is you take it totally saturated on one end, you put it in an oven dry it on the other end. In practice, we don't have saturated block walls. We don't have oven dry walls. So the value we get from the ASTM test is pretty high. For design, we're going to use about half of that. But still, we've got a pretty fair amount of movement in a 100-foot long wall. So we calculate our movement. The next step is we're going to design our reinforcement to limit our maximum crack width to 0.02 inches. Why do we do that? Well, 0.02 inches is about the limit that our surface applied water repellents can help us to keep water out of a wall. It's not visible, not real visible. And so, engineering, I tell you what, we can go through these calcs. There's a better approach though. NCMA Tech Note 10-3 has some design aids, a big table full of numbers. The key is you run down this table, like here I've got an arrow for an 8-inch block wall, right? Our 8-inch block wall here. Bottom line, if we're using 9-gauge joint steel right here, for an 8-inch partially grouted or ungrouted block wall, we're going to put in 9-gauge joint reinforcement every 16 inches on center. That's pretty standard. So every other course up the height of the wall. The other arrows down below, that's for a fully grouted wall. Need more reinforcement in there if we follow this engineered approach. And so we need actually 8-gauge rebar, or I'm sorry, 8-gauge joint reinforcement at every course, every 8 inches up the height of our wall. So I think the bottom line is, you know, we're used to putting joint reinforcement every other course, 9-gauge in our walls. Perfect. You know, this engineered approach really just proves what we've been doing for years and years. And remember, when we're detailing our control joints, this is a nice detail. Our concrete masonry control joint is really just a weak spot in our wall. We're going to attract movement to that joint. It's like you have a joint in your sidewalk. Walking down the sidewalk, those control joints attract movement. Here we're going to use a backer rod and sealant at the face of the wall, and that's going to keep water out of that joint. We can have rigid or semi-rigid materials in that joint. Remember, the block is pulling away from this joint, so if we need a fire rating out of that wall, we'll put a preformed gasket, ceramic fiber mat in there, and we can grout those joints. What do we do with our joint steel? We cut it. It's hard to see, but we don't run our joint reinforcement through our control joints ever. Bond beams, sometimes they're cut, sometimes they run continuous. So if you have a bond beam up here, talk to the engineer, because you know, at floor diaphragms, we'll run that steel through the wall or through that control joint. And that's okay. This control joint still works. It's still a weak point in the wall that attracts that movement. So expansion, shrinkage, right? This is, like I said, it's always on the test. Brick masonry expands or shrinks. This is the class participation component of today's seminar. Brick masonry expands, concrete block shrinks. You can follow, you can cheat, it's okay. So we're going to put expansion joints in brick masonry and concrete masonry putting in control joints. They're different. They're not the same. A control joint's different than an expansion joint. So let's get the terminology right. Got it? Now this is something I talk to contractors about these concepts as well, and when I'm talking to them, I pulled this out of one of my contractor certification classes and tell them, hey, if you see this in your spec, be aware this is going to cause you problems. Project spec says install control joints in concrete masonry at a maximum spacing of 25 feet on center. Why is that a problem? Well, number one, Mr. Contractor, it's making you the designer, shifting that design responsibility from whoever should be designing those control joints, usually the architect, and putting that on you. Plus, you got to think. You got to think about things like, where am I going to start? Do I start at the corner? Do I start 25 feet off the corner? Do I put them at windows, every other window? Listen, we should have elevation drawings. We should have them on plan views showing exactly where every control joint needs to go on our walls. So, as I stated earlier with the concrete block, we're going to start with putting control joints where we need them, at our corners. Usually I like them right at the corner, not within every 10 feet. Say we want it right at the corner. So if you've got an 8-inch block wall, I'll put that first joint right here at the corner, down here rather than 10 feet off, but that's my opinion. The industry says within 10 feet of the corner. Wall returns, offsets, intersecting walls, underneath shelf angles. A nice detail here right out of this tech note that shows you all the places where we want movement joints, control joints. What about windows? They're showing the control joint kind of stepping around our lintel bearing, if you follow it up here, right? Another approach is to put it vertical, maybe 8 inches off our window. I'll see some people put those joints, centered in the piers between windows. Whatever you do, the concept is just run them up. It's hard to draw a straight line with the mouse. There we go. But run them up and down, recognizing that we have stress concentrations that can attract cracks. So all of this 20 minutes of discussion about moving joints comes down to one slide. Brick masonry expansion joints, 25 feet max on center. Non-modular, we're going to go 25'4". Concrete masonry control joints, 25 feet in CMU walls. There are some references out there that want to cut that down to 20 feet in veneer. And again, we're modular is 25'4". Couple of other things to think about. We're going to have, again, split our walls up into rectangles with an aspect ratio of 1.5. Spacing between joints, 1.5 times the height of our wall. And finally, parapets, fences, areas with severe exposure, we're going to cut down that spacing by 1/2. Why do we do that? Well, they're seeing temperature, think about a parapet. It's seeing moisture on both sides of the wall. It's seeing temperature on both sides, so it's going to move a lot more than a vertical wall of a building. Fences, not conditioned space on the backside of that fence. So again, fences move around a lot more. Okay, designing for movement. Buildings move. Concrete, look at this concrete building. It knows how to move. Earthquake, liquefaction. I think it's in Japan. Fascinating. We talked about this concept of, I mentioned that we'll talk about wood later. Here we are on the wood part. I took a few slides out of a nice class for the Rocky Mountain Masonry Institute on podium type construction. Where we'll have concrete block or concrete first couple stories and then wood frame up above. There's an issue with what we're doing with masonry veneer these days, because building code now lets you go more than 30 feet above the foundation with brick veneer on wood stud. If you're using the 2022 version of our TMS code, I don't think a lot of places have adopted that yet, but it's coming. We can go up to 50 feet now. What's the issue there? Well, we just learned brick expands over time, right? Our brick veneer is expanding. We know that wood frame and wood stud construction shrinks over time. So think about the differential movement. And with that brick expands and wood frame shrinks, that can lead to very real movement. That's going to tip our roll-lock sills and our roll-lock caps back, and we see it in practice. It'll press us so much we can actually pop some of the sheathing off if it's not anchored correctly. So what do we do here? Well, there's again, I like industry publications because again, not just my opinion. This is the best minds in the industry have put together the Brick Industry Association. When was that published? Yeah, I want to say 2018, 2019. I can't quite see that, but since we can go over 30 feet, we can do that, but the code says we have to design to accommodate this differential movement. And this brick brief that was published by the Brick People several years ago tells us how to do it. It's got nice details, a nice process, and to summarize the process, here it is. I mean, most of our wood shrinkage occurs not in the stud part of the wall, like along the length of a 2x4, it doesn't shrink that much. It's the cross grain shrinkage that dominates movement of that backing. So if we have a sill plate, we're always going to have sill plates top and bottom of our stud wall, a double sill plate at the top. We're going to have a rim joist. So most of that movement, about 3/4 of the movement in our wall is taken up right at those floor lines. And it's a big number, 1/2 inch per story. So if you're going up 5 stories, 2.5 inches of potential movement between our veneer and our wood backing. That's a big deal, and it happens because when the wood comes out of the kiln, it's got a moisture content of 19%. I looked it up. In St. Louis, our equilibrium moisture content somewhere between 12 and 14%. So as that wood loses moisture, a lot of times that wood's in the wall already before it's fully lost all its moisture. It's shrinking quite a bit. So how do we deal with this? 5 stories tall, 1/2 inch per story, that's 2.5 inches of total movement we have to deal with. Number one, we're going to put in adjustable veneer anchors, right? These are these iron pintle types. You get the idea. Adjustable veneer anchors, right? What else? We're going to have some slip joints or some way to accommodate that movement, any kind of wall penetration or any kind of interaction between the backing and the veneer. So on top of our, let's see, on top of our window sill, we actually have a little metal sill with up to 2.5 inches of movement capacity. So as those two elements move differentially, we accommodate that movement. We're going to have a slip joint around any penetration. So a dryer vent or a bathroom exhaust vent, if it's going through our wood framing, going through our brick veneer, we need some type of a slip joint. Either I've shown it here in the veneer. You can also have that slip joint back in the wood framing as well. If we don't put those in, we're going to see things getting crushed, things getting moved, bricks getting dislodged. So be careful. You know, code lets us do certain things now that I don't quite agree with, but that's a discussion for another day. All right, what else? What other kind of transition? Let's talk about transition, detailing transitions with vehicles. We're not covering that today, but banding of masonry, different types of supports, concrete. And we'll finish up with a little discussion about residential. Now, I love this photo. I don't know, this wasn't a project of mine. I was just walking out into the local, I think it's a King Soopers, a grocery store, and we've got stucco up above, we've got a brick roll-lock cap, we've got a band of concrete block, and we have brick below that, and I love it. Look at this joint, this movement joint in between. We zoom in, well, what do we notice? Down at the brickwork, it's expanding towards that joint, that movement joint's compressed. The block is pulling away from that joint, so that movement joint there is expanded. And again, if you look close, we see a little separation here. Are we worried about that? This is just a veneer. Are we worried about that causing a structural issue? No, because we got our veneer tied to the backup. That's good. Okay. What about moisture? Better have your cavity wall details bomb-proof. You better get all of your cavity wall detailed properly, flashing weeps down at the base. And there are a couple recommendations in the industry about how to control that type of a movement. If we're putting a band of concrete block, which is shrinking, in the middle of a brick wall, which is expanding, we're going to put extra wall ties within 1 foot, within 12 inches of the top and bottom of that band. That's just to make sure that any cracks or separations don't affect the stability of our veneer. We're going to use joint reinforcement every course of our concrete block band. So here, just top and bottom. We're going to drop our expansion joint spacing down from 25 foot forward to 20 feet. And well, let's go back. And we're going to use a softer mortar, like a type N mortar. You know, it's a great choice for veneers anyways. That softer mortar is better able to accommodate movement without cracking. So, you know, another industry detail that's out there is this one. They're putting sealant. Here's our concrete band. We're going to rake back the mortar above and below and put a sealant joint in. We're going to put a little slip, a bond breaker like flashing paper or poly above and below, because we know things are going to move. We're going to put in a slip joint, sealant, all these things, flashing and everything. I've got a better solution. What's the better solution? Just use the same material. Okay, we can get some really nice looks with concrete block. We've got smooth face block, we've got split face, different colors, different textures on the outside. All of that on the left and right, those facades are built entirely out of CMU. We can do the same with brick. You know, recessed courses, different colors of brick. So you can mix brick and block. You can mix stone with brick, stone with block, but the better idea, the more foolproof way of doing things is just use the same material all throughout. You know, just projecting in recessed courses, you know, here, same brick all throughout, but we get a nice accent to our, let's see, our sills, our jambs, our window heads by just pulling that brick out from the wall a little bit. And even imitating quoins at the building corners. Again, just a little bit of a projection. The thing to worry about, to think about, all of these ledges tend to collect water. We'll tell the mason to put a little mortar wash on there, you know, a little slope to the mortar joint to shed water off that cap. How much of a projection are you going to put? Got to be careful if you're not using 100% solid brick. Our brick cores, those holes in the brick, can be pretty close. They can be up to 3/8 or 3/4 of an inch away from the face. So we'll want to make sure that we limit our projections to somewhere in the 3/8 to half an inch range. Okay. Go more than that, you're going to expose those brick cores. And it looks bad. Let's water into our wall. So limit our projections to about half an inch max. 3/8 even better. Okay, what other kind of transitions? Well, we have transitions between different foundation systems. High-end home, structural foundation under the house, little wing wall out here, that's more of a landscaping foundation. What's going to happen along this interface? Things are moving, right? We know what's going to happen. Detail it in. I would have detailed in a movement joint here, right at this interface, instead of, now the cracks opened up. And we can just tell by the way the cracks form that wing wall is just tipping out. Again, not a problem with construction, not a problem with the structural design. We know what's going to happen. Let's put a movement joint in there to accommodate it. Thin brick on wood frame on the left, thin brick on the CMU backup on the right. Different foundations. If we zoom in, actually, you see a movement joint, that's great. It's kind of an odd placement, right? It's kind of halfway, a lot of brick cuts here. Why do they do it that way? Well, this joint was cut in after the fact. Every single one, there's like 30 homes in this subdivision, and every single one of these wing walls, there's a crack that's opened up there. And again, no big surprise to us, because you all know these things now. But yeah, cutting in a movement joint, Mother Nature put one in right here. We just cut one vertically to accommodate that future movement. Would have been better to design that movement joint in to start with. So if we have different support conditions, it's actually a building code requirement, oddly enough. If we're supporting brick veneer or any kind of veneer off the foundation, like we have in this facade, all those loads go all the way down, supported by the foundation. What about this brick here and here and here at the return? What's supporting that brick? Well, if we look in close, well, we have a shelf angle on top of every balcony slab. That's great. That's a good solution. We don't want our brick to be sitting on that balcony slab where it's going to move around. But right around that corner, that brick's supported by the foundation. So we have different runs of brick, different heights. We have different support conditions. The shelf angle's riding along, in this case, with the wood framing. And so we get a crack. And I don't know, if you're sitting up front, you can see it. There's a crack there. The solution, this was already built. We came in and something always happens in translation. Are we putting our movement joints there? No. Draw this in. Movement joint should be here, right around the corner, right where that crack occurred. We run it here. We don't need it in the first story because all that brick's resting off the foundation. So if you're designing a building, you've got brickwork that's running from the foundation up to the top of the building, around the corner at your return, and supported on shelf angles, always put a vertical movement joint between the two. Backer rod and sealant, keep out water. Transitioning to concrete, there's let's see, there's like 3 wrong things in this image. This is a manufactured stone veneer, an adhered veneer. For whatever reason, the veneer went on the building first. The concrete contractor came in and put in the slab later. That slab's moved. You can see these little ghost lines, right? Concrete slab used to be up here. What are our problems? What should we not do in this image? We're never casting concrete against brick or block or stone or anything important. Don't cast it against a masonry. We're going to put a little separator, right? A little fiber expansion board in here. And here we've got brick. We've got brick, a veneer below grade. Brick can handle that. It's durable enough. We're grouting the drainage cavity behind that brick below grade, putting our flashing and weeps right at grade. So that's issue number 1. Always have a separator. What's issue number 2? Well, they should have installed this adhered veneer like this with actually a separation between concrete and the veneer material itself. And these are building code requirements. If we have an adhered veneer, we're required to put a clearance to grade 4 inches. 2 inches above paved areas, or ½ an inch above a walking surface like a slab or pavement, as long as that slab is tied into the home's foundation. If it's not, we're back to this 2-inch idea. And I don't know what it is. I think designers, especially in high-end homes, homeowners, they don't want to see any of that concrete exposed. You can kind of work around it, but honestly, anything that's within 4 inches of grade or less is in my mind sacrificial with an adhered veneer, because water's going to get in. It's going to affect the bond at the back of that stone. It's going to affect our wall conditions. And I like this image. Big old stone, right? Well, the stones always move downhill, and make sure there's separation between our landscaping boulders and our wall as well. That's caused this little unit here to dislodge and kind of move down. So what are we going to do? Well, we're going to provide a separation from grade. If you want to get around that, I've not allowed it. I've kind of lived with it on a couple projects where, just telling the contractor that, listen, you can put stone down to grade like we see here, but that stone is going to be sacrificial. It's going to take more maintenance. It's probably a couple stones are going to fall off every year. You got to deal with it. And that transition from the backing being a wood framing to a concrete block, concrete foundation wall, we're going to stop our drip edge right here. We're going to install a drip edge right at that transition. Below that, the adhered veneer is stuck right on the face of the concrete foundation wall. Different system altogether. So we separate those two systems with our weep screed in our adhered veneer backup. What are we doing with transitions to windows, wood siding, stucco? Very vulnerable areas, and what goes in at this point is, well, shouldn't be mortar. We call it a transition. At that transition, we'll call it an isolation joint. That could be as simple as a 1/4 inch space, 1/4 inch wide space, with backer rod and sealant. Okay, we know these materials are going to move differently, so we'll put in an isolation joint around our windows, around our other materials, just similar materials. And honestly, when you look at these situations, here's a horizontal transition, adhered stone veneer below to wood siding above. It's not really a design issue. It's more of a coordination issue. So the general contractor is dealing with carpenters, finish framers. Who's putting on the weather resistant barrier? Sometimes it's a GC. Who's putting on the stone veneer? Okay, and at those interfaces, we really need a good discussion. And if you're having a pre-construction meeting, that's a good time to bring it up. Who's putting in this flashing? Are they going to put it in right? Is this right? No, it's just put onto the face of the WRB. We want that building paper or this Tyvek, whatever we want to call it, to lap down over the vertical leg of that flashing, so any water getting behind our siding gets caught by that flashing and directed out of the wall system. So again, this little vulnerable area right at this transition from bricks, stone below to siding above, a lot of things happening. It's a coordination issue. Let's make sure that the general contractor's got that covered. Isolation joints, when we transition to windows, siding, trim, item number 3, here's our isolation joint. And again, nothing magical, about a 1/4 inch space there, backer rod and sealant. And this detail comes out of, by the way, you can go to, I do a lot of work, I'm from Colorado. I work with the Rocky Mountain Masonry Institute a lot. We've got on our website this free downloadable PDF design guide for Colorado masonry systems. This detail actually shows a secondary kind of barrier back here, because this is a vulnerable spot. Actually having a fluidipide vapor barrier down here and a little flashing membrane wrapping the corner, so that we're keeping water out of our building, out of the insulation. And it's important, as we're designing these details, is again another little detail out of this Masonry Systems Design Guide, that shows, I think a nice graphic shows where our water barrier is. That's behind our veneer at the back side of our drainage cavity. That's our air barrier, that's our water barrier. In green, at the face of our wall, that's our water shedding surface. You know, and I don't know, I get a lot of people wondering about, you know, do I worry about water and air getting in behind the veneer? We know it's going to happen. We're designing our flashing at the base of our drainage cavity, we're designing in weeps, again, to get that water out of the system. Our water and air barrier is at the back side of our cavity, right back in here. A detail from the Stucco Manufacturers Association. I don't love this detail, but on the other hand, if you have a wood framing that's all the way up, that's already built up, we've got stucco coming into our concrete block. This is a chimney. Here's our casing bead that's at the end of our stucco run. They've actually wrapped a piece of flashing, you know, that comes down into the face of the block and adhered it to the face of the block with mastic. I don't love it because it's visible, but again, maybe that's up above the roof line or somewhere where it's not so visible, hopefully. But the concept is protecting that vulnerable area with an externally applied flashing set in the mastic at the face of the block. What's another approach? Well, design in an actual flashing system so that that's installed with the block to transition over the face of the sheathing into a regulator, into a slot cut into the block. Couple more last little concepts: tops of walls, parapets, and coping. Let's see. We learned that concrete block shrinks, right? It responds to temperature, responds to moisture. Our veneer is going to shrink a lot. Our structure probably moving a little bit less because it's conditioned space and all that. So we have an anchor here we're anchoring our parapet cap to the structure. We're providing a movement joint, again, about a 3/8 inch back rod and sealant at the face of the wall. So that parapet cap's attached to the structure, the veneer can move independently, and that's what we want. Wonderful. So parapets and coping, another little detail. I think it shows it a little bit better, but it gives us an opportunity to think about one more thing. There's our anchor. Here's our movement joint up in front, underneath our parapet cap. What are we going to do with the joints between our coping units? What do we want to do there? Do we put mortar in those joints? You can, but think about our coping stones are usually 2 feet to 3 feet, sometimes up to 4 feet long. That doesn't provide us with a lot of joints that accommodate any lateral movement. So mortar between parapet caps always cracks, lets water in. I think a better solution are these top two, right? You can put mortar in there, but we're going to rake it back, put a sealant joint, back rod, or don't even bother putting mortar in the joint at all. We got sealant, back rod here. Again, the most durable joint is one that keeps out the water. If we just put mortar in between those wall caps like we see here on the bottom, that's incorrect. Those joints are going to open up over time and let water in. You'll see some staining and all that. So we've learned a bit. Again, that's kind of my editorial comment, and I think when I put a lot of this material together a couple of years back, I'm defending a lot of masons in our area for these things that they're doing because they're not shown on, the movement joints, isolation joints, they aren't shown on the plans, aren't shown on elevations. If you leave it up to the mason, they'll typically put in just a little mortar joint between the brick run and the between the brick and the siding there. So bless their hearts, they're trying real hard, they're doing what they know how to do, and unless they're directed to do something different, like put in an isolation joint, a gap between the brick and the siding, they're not going to put it in. Okay? Generally, they just butt the brickwork right up to the siding. Better solution, have an isolation joint, design it in there. Do we really need it in all of our residential applications? Well, we've been through the calculations, we can run through it. We got 1 foot 10 inches of brick at this little return. Otherwise, multifamily residential, big, long, 100-foot long garage unit. We can calculate if we got 1 foot 10 of brick, the total design movement potential is about 2/100 of an inch. That's the width of a staple, not a construction staple, a paper staple, very, very small. So we can get by with a little bit of movement. We're not going to damage the siding. We're not going to damage the brick with that level of movement, but we have the potential for water to get in. So what are we putting in there? Show it on your details, show it on your elevations. I want an isolation joint, a 1/4 inch wide, 3/8 inch wide, backer rod and sealant in there to keep water out of that condition. So there we go. Lots of little details, lots of little things to think about. We learned that brick expands, right? We learned that block shrinks. And we learned a little bit about moisture management, all these good little things. There is some good info. We looked at some brick industry technical notes. We looked at some CMHA tech notes as well. A couple details from IMI and some details out of our Colorado design guide. And yeah, it's a lot of things to think about. I'm sure there's some questions. We can ask questions, or I'll stick around for as long as it takes if you want to talk about things. But appreciate your time, everyone. Any questions, or anybody want to talk about anything? Just in general? Weather? Well, thanks for your time. Appreciate it.
Thank you, Michael. Thank you so much.
You bet.
Have you pick our winner for your book?
Oh, we have a winner, right?
Yes.
I get to
Yeah,
pick?
You get to pick.
All right. One of these people gets a free book, and it is Discover Hazelwood.